Okay, today we're talking about uniform circular motion, and we're going to work through the examples that you saw in class. Today we haven't had this class yet, so I hope we get through most of these examples, but if not, then the others will be there for you to practice on. But right here I'm going to work through all of them. Again, these are the examples in the PowerPoint slides. Okay, so first example. Suppose the coefficient of static friction between the road and the tires on the road is 0.60 and the car has no negative lift. What speed will put the car on the verge of sliding as it rounds a level curve of 30.5 with that radius, 30.5 meters? So go ahead and write what we know down. And what else? Radius equals 30.5 meters. Okay, so drawing a picture. Let's draw this little picture here. Got my car on the road. It is moving with some velocity in that direction. Well, it's moving in that direction at that instant. You know, later on, the velocity will be in that direction. But the velocity is definitely changing because it's changing direction. The magnitude stays the same, but the direction changes, meaning there must be an acceleration. What is that acceleration? That is the centripetal acceleration, which is the acceleration towards the center. So we're viewing this curve as a big circle, that being the point. So what causes that acceleration? Well, that is the centripetal acceleration. And here the force of friction, that's static friction in that case, is serving as a centripetal acceleration. So if you remember, centripetal acceleration is not a specific force per se, it's just a role that a force is playing. So with the satellite orbiting around the Earth, the gravity is going to serve as the centripetal acceleration. In this case, friction is serving as centripetal acceleration, so we can say centripetal force, excuse me, I was saying centripetal acceleration, I meant centripetal force. Centripetal force is, that role is being fulfilled by the frictional force. Because the friction here is the only thing keeping that car from moving in the direction of the velocity as continuing on in that direction. The friction is what causes the car to move around the circle. So if I draw another diagram, if we consider this like the X and Z axis, we're looking at the car from overhead. But now I'm going to draw another free body diagram where I'm looking at, say, the XY axis. In that case, gravity is pulling the car downward, the normal force is pulling the car upward, and the centripetal force is pulling the car towards the center. So again, X and Y axis. And that centripetal force is equal to the frictional force. So this is view from road level. And this is view from above. Okay, so let's sum up our forces here. In the X direction, and I'll sum up the forces in the Y direction. I'm not going to worry about the Z direction because that's not really going to be important here. It's just a two-dimensional problem. I drew this image with the Z direction just to give us an overview of what's going on in the problem. So in the X direction, you have the force of friction, and that's it, right? And we know that equals the centripetal force. In the Y direction, we have the normal force and we have the negative force of gravity that's pulling the car downward into the track. Summing up, the sum of forces in the X direction equals, again, force of friction, which equals centripetal force. And again, this equals mass times acceleration, which equals 0. I'm sorry, it does not equal 0 because it is a net force. Excuse me. That does not equal 0. On the other side, though, the sum of the forces in the y direction equals the normal force minus the force of gravity, which equals may, which does equal 0 because the car is not lifting up off the track and it's not sinking down into the track. Okay. So now we can say, and I forgot the little s there, that's the force of static friction, equals the centripetal force. It's also important to note that this is the maximum force of static friction, because the question, you see, what speed will put the car on the verge of sliding as it rounds a curve. So we're talking about that critical point right before the car starts sliding. So it's got to be the force of static friction. Okay, so expanding these, mu s Fn, that is just how we expand the force of static friction, maximum force of static friction. And the centripetal force is mv squared over r. And if you remember, this equals mass times acceleration because it is a net force. Mass is mass, and acceleration, centripetal acceleration, is v squared over r. But we're not going to deal with that. We're just going to work from here. So over on the y side, the normal force equals the force of gravity. So we can plug that in. Mu s Fg equals mv squared over r, or mu s mg equals mv squared over r. M's cancel out. So now we're left with mu sg equals v squared over r. Or if I flip the equation, v squared equals mu sg times r. I multiplied each side by, well, I'll write that, each side by r. And v equals square root mu sg r. Which equals 0.60 times 9.8 meters per second squared times 30.5, whoops, I'm off the page, I'm sorry, meters. Evaluate all that. The answer is 13.4 meters per second. All right. Moving on to the next one. Well, I guess I'll just use the back. Okay, so this is the tough one. Civil engineers generally bank curves on roads in such a manner that the car going around the curve at the recommended speed does not have to rely on friction between its tires and the road surface in order to round the curve. Suppose that the radius of the curvature of a given curve is 60 meters and the recommended speed is 40 kilometers per hour. At what angle theta should the curve be banked? Well, I'm going to first write down what we know. So the radius equals 60 meters. The velocity equals 40 kilometers per hour, but we need to convert that into meters per second. Times 1 kilometer, kilometer is 1,000 meters, and 1 hour equals 3,600 seconds, and that equals 11.1 meters per second. When you work these problems, if you just want to convert it in Google, that's fine. I mean, I trust that you can do unit conversions now. All right, so draw our curve. It's at an inclined plane. We have the force of gravity working downward. We have the normal force working upwards. If we did have friction, it would be in this direction, but we don't, because the problem states that we're not going to rely on friction. to go around the curve. We're just going to rely on the banking angle. So, as we usually do, the next step is to draw a free body diagram. You'll notice something a little weird about this. Before, remember, we had to tilt the axes. Okay, well, in this case, we're not going to tilt the axis. We're just going to leave the axes as they are, and you'll see in a second why. G, and where is theta? Oops, theta is right here. So that would make, let's see, that would make this theta, which would then make that theta as it usually is, and that would also be theta. So all I did here is, as usual, we remember that backside is equal to the angle of elevation theta. So if you label that down here, then you know from geometry, two straight lines cross each other. These are, I forget the term, but they're opposite angles, I believe. So they're equal. So move it down a step. Okay, so this is F and Y, F and X. And the reason we didn't tilt the axes is because the overall strategy here is we want to know the portion of Fn, the normal force, that serves as the centripetal force. Because remember, the curve you can think of as a circle in that plane. So the centripetal force is going to act parallel to the ground, if you will. So by leaving the axes untilted, just as they are, I can break the normal force into components, both vertical and parallel to the Earth's surface, which then lets me set that equal to the centripetal force. So summing up all of our forces, like usual, we have Fnx, which equals Fn sine of theta. Why is that? Because this is opposite to the angle, so we'll use sine of theta. I can write it out if you want. Sine of theta equals opposite Fnx over hypotenuse, which is Fn. So Fnx just equals Fn sine theta. In the y direction, we have Fny, which equals Fn cosine of theta, and minus Fg in the other direction. So Fny minus Fg. Okay. Sum of the forces in the x direction equals mass times acceleration in the x direction, which does not equal 0 because we only have one force. There's nothing else to cancel it out. And we know there's going to be a net force because there's a centripetal force. So the sum of forces in the x direction just equals Fn sine of theta. And you can say that equals max, so Fn sine of theta equals m times the centripetal acceleration, v squared over r, which is just the centripetal force, mv squared over r. In the y direction, Fy equals Fn cosine theta minus Fg, and we know that it equals may, which we know is equal to 0 because the car is not floating off the track. It's not sinking in the track. There is no acceleration there. Fn cosine theta equals g. Okay, here's the tricky part. Here's the part people aren't going to like. We have all these unknowns floating around. What we can do is we can take equation 1, and we can take equation 2, and we can divide 1 over 2. So that equals Fn sine of theta equals mv squared over r, and we're going to divide that whole equation by Fn, whoops, not nn, Fn cosine of theta equals mg. Well, you'll notice immediately from this that the two normal forces cancel out. Sine over cosine, which you may remember, where should I write? Here. Sine of theta over cosine of theta equals tangent of theta. You're going to have that there. These m's cancel out. So you're left with tangent of theta equals v squared over gr. That's an important equation. That was derived for you in the book. If you're wondering why sine over cosine equals tangent theta, well, just remember that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and that equals tangent, which is opposite. Well, what does that equal? Let's prove it. Hypotenuse cancels out, so that equals opposite over adjacent, which just equals tangent of theta. So now that we have this special equation here, it's just simple to take the, inverse tangent of each side. The inverse tangent cancels out tangent, so theta equals inverse tangent of v squared over gr. Now we can just plug stuff in. Let's see. 11 meters per second? 11.1 meters per second. And this whole quantity is squared times 9.8 meters per second squared times r, which is 60 meters. And then theta is equal, when you calculate all that out, it is 11.8 degrees. So let's see what the next one is. Okay. Oh, there's this page. So the next example says, find the proper banking angle for cars moving at 22 meters per second to go around a curve of 304 meters in radius without friction. Okay? So let's write down what we have. Cars moving at v equals 22 meters per second. The curve is 304 meters in radius. Find the theta. Find the angle theta. Well, I hate giving you super specific equations that you have to memorize or use or whatever. I would rather give you physical principles by which you could derive equations. But this was kind of a difficult derivation. So I will just go ahead, and the book gives this to you as well as an equation to know. So I'll go ahead and say tangent of theta equals v squared over gr. And we'll just use that as the starting point for problems given giving a banked road. But it is really informative to go back and derive this equation, because it's if you can derive the equation, then you can work all the problems without any issues at all. If you can't derive this equation, you may not be able to apply it either. But that's just, yeah. Okay, so in this case, theta then is just equal to the inverse tangent of v squared over gr. So that equals tangent -1 of 22 meters per second squared over 9.8 meters per second squared times 304 meters. Plugging that all in, theta equals 9.23 degrees. So the second part, that's part A. The second part says, if the road were not banked, what coefficient of friction would be needed between the tires and the road? Well, so this is very similar to the other problem we had, where we had the car, the first problem. The force of static friction serves as the centripetal force. Velocity is that direction. Or we can draw the free body diagram. Okay, and well, that is actually a force of static friction, which equals the centripetal acceleration. Let me draw. And we'll sum up our forces in the x direction, and we'll sum up the forces in the y direction. In the x direction, that equals the force of static friction. Well, I'll just leave it at the force of static friction for now. And in the y direction, we have the normal force and we have the negative gravitational force. If we sum in the y, that equals the normal force minus the force of gravity, which equals mass times acceleration in the y direction. There is no acceleration in the y direction, so that equals 0. And the normal force equals the force of gravity. In the x direction, all we have is the force of static friction. That equals max, and that does not equal 0. We know because that's the only force there acting, so it has to be the net force. But also, we know that this car is going to be changing direction, so it has to be accelerated. So there has to be a net force. That net force is the force of static friction. Well, I should actually say, should mention it's the maximum force of static friction. Because well, let's just leave it at there for now. Equals max. And so mu s Fn equals m times the centripetal acceleration, because in this case this acceleration is inward, in v squared over r. So it equals mu s Fg equals mu s mg equals mv squared over r. Not r squared, excuse me. It's not gravity. It's just mv squared over r. Well, m's cancel out of each side. Divide each side by g. V squared over rg. Or it equals 22 meters per second squared over 304 over 9.8 meters per second squared. And mu s equals 0.162. So what we've done here, I just want to recap. We're traveling at a given speed. So we found the maximum force of static friction. Why maximum? Because that is that is the lowest amount of friction that you can have, the lowest amount of static friction that you can have to keep a car moving this speed in the circle. Yes, you could have more static friction if this were, the coefficient here could equal 0.5 or something. But this is what you need to create the maximum amount of friction needed for this particular speed. All right. Okay, so this one's a little tricky. A racetrack has the shape of an inverted cone, as the drawing shows. The drawing is in the PowerPoint lectures. On the surface, the cars race in circles that are parallel to the ground. For a speed of 34 meters per second, at what value of the distance d should a driver locate his car if he wishes to stay on the circular path without depending on friction? The angle of elevation is 40 degrees. No, that's a terrible drawing. And I believe that is D. Okay. So the car's racing around the circle, and it's being held up there by centripetal force. Okay, so let's look at just a blown up view of the car itself. It's got gravity, it's got the normal force, it's got the force of friction. So we could go and derive that expression you saw before, but you are already given this equation, so we'll just start with this equation. This is for banked roads. Well, the problem gives us theta equals 40 degrees. The problem gives us V equals 34 meters per second. We don't have R, and we have G, but we also need to get to D. So we're probably going to have to put R in terms of V somehow. So looking at, just draw a triangle here. So let's say the car is this is D, up to the car. Now the cone could go on further, but we're just going to deal with this part of the triangle. So this is the cone. Could be really big, but let's go to D. Okay, so we know this has to be theta. So that means R, the radius of the circle that it makes, is going to be equal to the bottom leg of this triangle. So cosine of theta is equal to adjacent is R over hypotenuse, which is D. So D equals R over cosine of theta. I could actually solve this for R instead. R equals D cosine theta, because that's going to come in to this equation here. Tangent of theta equals V squared over d cosine theta times g. And we're solving for d, so multiply d times each side. D tangent of theta equals, that cancels, b squared over cosine theta g. And divide each side by tangent of theta. B squared over tangent of theta cosine of theta times g. And we can plug in d equals v squared 34 meters per second squared over tangent of 40 degrees times cosine of 40 degrees times 9.8 meters per second squared. I don't have a calculator on me, but you can calculate this out, no problem. So this is just, when you're given this equation for banked roads, then this is really simple. All you had to do was relate D to R and plug in. But do know how this equation came about. Okay, so we'll look at the next one. Get my papers organized. So the turns at the Daytona 500 have a maximum radius of 316 meters and are steeply banked at 31 degrees. Suppose these turns were frictionless. At what speed would the cars have to travel around them? Real simple thing again. Radius equals 316 meters. Steeply banked at theta equals 31 degrees. Tangent theta equals v squared over g r. And the question wants to know at what speed, so v squared equals gr tangent of theta. And v equals the square root of gr tangent of theta, which is 9.8 meters per second squared times 316 meters times tangent of 31. And we're back. So I found a problem that's a little more interesting. I'm going to try to work this into the lecture slides if I haven't done that already and forgotten. Anyways, the car is safely negotiating an unbanked curve at a speed of 21 meters per second. I'll go ahead and write that down. It's unbanked, remember. The road is dry, and the maximum static frictional force acts on the tires. We don't know what that is. So suddenly, a wet patch in the road decreases the maximum static frictional force to 1/3 of its dry road value. Well, I guess I'll call that mu S1, and then mu S2 equals 1/3 mu S1. Or I guess I could say dry. That makes more sense. USW is wet. By how much must the driver slow down to safely negotiate the wet curve? Okay, so force of gravity is working downward. The normal force is working upward. The force of friction then equals the centripetal force. So summing up our forces, F of x, F of y. F of x is just F, which equals the centripetal force. F of y equals Fn, and gravity is negative. Summing up the forces in the x direction, that is just equals friction, which equals max. And summing up these forces, Fy equals Fn minus Fg equals may, and we know that equals 0 because there's no motion in the vertical direction. So the normal force equals Fg. The frictional force equals max, where acceleration is centripetal acceleration. So mu s N equals mv squared over r. We have the normal force over here, so that we can say that equals mg. So mu s mg equals mv squared over r. M's cancel. Mu sg equals v squared over r. The question's asking at how much you'll have to slow down, so we're going to need to solve this for velocity. So v squared equals r mu sg. V equals square root of r mu sg. So this would be, if we went to say, okay, so what then is the ratio of the velocity from the dry to velocity when wet? Well, that's going to equal square root of r times mu s dry g over square root of r mu s wet g. And that would equal square root of r mu s dry g over the square root of r. Remember, mu sw is just 1/3 mu s dry times g. And that d is a little too big. It looks like a variable. So you notice that r's cancel, g's cancel, mu s cancels. Well, that's mu sd in each case. So this equals square root of 1 over 1 over 3. That 1/3 is the only thing left. Or I can say v dry over vw equals square root of 3. Or you could say the velocity when wet is 1 over square root of 3 times the velocity when dry. So your speed must be reduced by a factor of 1 over the square root of 3. Of course, you could plug that in and say 1 over the square root of 3 times 21 meters per second. Do I have that? I don't have that calculated, but you can calculate that number out. So what's the next problem? All right, where are we here? Determine the speed of the Hubble Space Telescope. Oops, let me get this straightened up. The Hubble Space Telescope orbiting at a height of 598 kilometers above the Earth's surface. What is the period of the Hubble Space Telescope? Well, let's draw a picture first. Let me draw it a little differently. This is the radius of Earth, and that is, let's call it h, height, where h equals 598 kilometers. Above the Earth's surface was the period at the HST. So if we look at the free body diagram at any point, force of gravity works downward, and that's pretty much the only force, right? And we'll say that's positive y direction. So summing up the forces in the y direction, we just have force of gravity. And that's going to equal ma, as it always does, because it's the net force. But we know that's m times, this is also serving as the centripetal force. So the centripetal acceleration is v squared over r. And gravity here is no longer just mg because it's above the surface of the Earth. So then we have to use Newton's law of universal gravitation for r squared. In this case, I use m sub t, so that defines the mass of the telescope, and me is the mass of the Earth. We can first simplify this equation a little bit. The mt's cancel out, that r cancels out, so I've got g, mass of the Earth, over r equals v squared. Now the problem asks us, what is the period of the Hubble Space Telescope? We know period equals 2 pi r over v. If I wanted to, let's say, solve this for v equals 2 pi r over t, I could take that and plug that in. So gme over r equals 2 pi r over t squared. Now we're going to have to solve all this for t. So, of course, I'm sure you realize this equals 2 pi r squared over t squared. So just multiply each side by t squared. Cancels that out. So t squared times g me over r equals 2 pi r quantity squared. Now I'll multiply each side by r over big G times mass of the Earth. So then t squared equals 2 pi r quantity squared times r over big G times mass of the Earth. We can simplify this a tiny amount. 2 squared is 4, pi squared is pi squared. R squared times r is r to the third. Big G, me, that's t squared. And I'm sorry, I just realized we're going to have to take the square root of all that stuff. 4 pi squared r cubed over gme. We can take the square root after we just squared 2 pi. We can take it out from the radical by taking the square root of 4, which is 2, and pi squared, which is pi. We don't want to deal with that r cubed. Just leave that under the radical. Okay. So we're almost to the expression, but we've got one little thing to do. We've got radius cubed, but radius equals radius of the Earth plus h. See, this is r. That is the radius of the circle that this telescope is making around the Earth. So t equals 2 pi times the square root of radius of the Earth plus h cubed over g me. Plugging stuff in, 2 pi times the square root of, what was the radius of the Earth again? 6.37 times 10 to the 6th meters. And height is 598,000 meters because it's given to us in kilometers. Divide that by the gravitational constant, 10 to the negative 11th, newtons, kilograms, was that kilograms squared per, I forgot what the constant units are again. I think it's kilograms squared per meter squared. And the mass of the Earth is 5.97 times 10 to the 24th kilograms. That gives us a period of 6.05 times 10 to the third seconds, or that's like saying 1.68 hours. Okay. So this one, if you look at the picture in the lecture, you'll see you've got a space station that is rotating. There's a guy standing on there. And there's going to be a centripetal force that makes it feel like gravity. This velocity goes around. So this asks, at what speed must the surface of the space station move so that the astronaut experiences a push on his feet equal to his weight on Earth? Well, our free body diagram would just look like this. Centripetal force. That is the net force. So I can write the centripetal force is equal to F sub g, little g, which is the force of gravity on Earth, or m times g. That's only because the problem asks us to make the centripetal force equal to the force of gravity on Earth. V squared over r. M's cancel out. So v squared over r equals g. V squared equals gr. V equals the square root of gr. So v equals the square root of 9.8 meters per second squared times the radius, which is, but we're given the radius, 1,700 meters, and v equals 129 meters per second. Simple enough? Let's just throw that piece of paper away. Let's get it on the floor. So a penny sits on a rotating disk a distance of 0.15 meters from the center of the disk. The period of rotation is 1.80 seconds. What is the minimum coefficient of friction needed to allow the penny to rotate along with the disk? Got a disk rotating, some velocity. We are distance r away, where r equals 0.150 meters. Drawing our free body diagram on the penny, we have F sub c, centripetal force. Well, that's the overhead view, but if we wanted to look, from the side, we have force gravity and the centripetal force. Maybe let's assume the penny is right here. So that this matches our free body diagram. Now the reason we have to take that free body diagram from the reason we have to draw this on the edge is because we're involving friction now, which is going to involve the normal force. So we have to look at that plane view, that view from the plane of the disk. And what does it say? What is the minimum? We know the period equals 1.80 seconds. So summing up the forces in the x direction and summing up the forces in the y direction. In the x direction, let's call this direction the positive x direction. It doesn't matter. And this is the positive y. So you just have the centripetal force, which equals the force of friction, because it's friction that's holding the penny in place. We have the normal force, we have the negative gravity, which is negative mg. I just went ahead and put mg in here. So sum of forces in the x direction equals, well, say frictional force, which equals centripetal force. That does not equal 0. The sum of the forces in the y direction equals Fn minus mg equals 0. Normal force equals mg. The frictional force equals mu s Fn, which equals the centripetal force of mv squared over r. Fn we can plug in from over there. Mu s mg equals mv squared over r. M's cancel on each side. Mu sg equals v squared over r. And the question is asking what was the minimum coefficient of friction, or mu. So mu s just equals v squared over rg. Now here's the only tricky part. We're not given the velocity, we're given the period, and we know that's 2 pi r over v, where v equals 2 pi r over t. So we can plug that into our equation, and mu s equals 2 pi r over t squared over rg, which equals 2 pi times 0.150 meters over 1.80 seconds over 0. Well, I didn't realize we had 2 r's here. We could have canceled one of those out and made it look a little prettier. 9.8 meters per second squared. If you calculate all that out, you come to 0.187 for mu. A satellite moves on a circular orbit with Earth, whose radius is 6.7 times 10 to the 6th meters. A model airplane flies on a 15-meter guideline in a horizontal circle. The guideline is parallel to the ground. Find the speed of the plane such that the plane and the satellite have the same centripetal acceleration. Okay, so we've got a person with a model airplane. And this airplane is flying around in a circle. And R, I'll call it RA, R of airplane, is 15 meters. We also have, this is Earth. And we have a satellite going around in a circle. And what do we know about the satellite? We have the radius of the satellite. Well, we have the radius of the orbit. Okay. Find the speed of the plane such that the plane and the satellite have the same centripetal acceleration. Well, what we know here is that the centripetal, well, let's just deal with centripetal force in this case. So we have the centripetal force, which equals mv of airplane, mv squared over radius of airplane. And we also have the centripetal force down here, which is mv satellite squared over radius of satellite. We don't have the mass of the satellite or the mass of the plane. So let's just, instead of worrying about force, let's just worry about centripetal acceleration. ACA equals mVA squared over RA, and acceleration, well, centripetal acceleration of the satellite is just Vs squared over Rs. Oops, why did I put the m back in there? I was trying to get rid of the m. We also don't have the velocity of the satellite, and we must find the velocity of the airplane. So since we don't have the velocity of the satellite, what we also must realize is that the centripetal acceleration is equal to the acceleration due to gravity, which is just going to be equal to g mass of the Earth over radius of the satellite's orbit squared. So I want to set these two equal to each other. So VA squared over RA is equal to G mass of the Earth over radius of the satellite squared. And then I can just multiply each side by the radius of the airplane. Oops, don't scratch that out. Scratch that side out. So V squared equals GME RA over RS squared, or V is just equal to square root of GME RA RS squared. So if we plug stuff in, well, this is 6.11 times 10 to the negative 11th newtons. Oh gosh, I always forget that. Kilograms per meter squared, I believe. Check me on the units. Mass of the Earth is 5.97 times 10 to the 24th kilograms. Radius of the airplane is 15 meters. Radius of the satellite's orbit is 6.7 times 10 to the 6th meters squared. And looks like I did not calculate that out, but you can calculate that out if you want to. This is the important part. You find that expression. Okay, those are all the examples that I have from centripetal force. So if you understand all of those examples, you should do fine on the homework.